pursuing my master's degree on network security at Özyeğin University. And today I will be talking about our research paper, SHAPEIoT, which proposes a secure handshake protocol for IoT devices for device discovery using physical unclonable functions. And also to maintain the security of the network, it uses blacklisting and real-time anomaly detection using machine learning. The outline of my presentation will be as follows. And if you have any questions, I would be glad to answer them at the end of my presentation. So starting with the motivation, IoT devices has gained a lot of popularity in the past couple of years, and we use these devices every day in our everyday lives, perhaps even without realizing it. And to be able to recognize and utilize the potential of IoT devices, secure discovery and access control is essential. However, IoT covers a very wide range of devices with different computational complexities, and not all of them are equipped with means to protect themselves from malicious malware or network attacks. With these in mind, this paper proposes a lightweight handshake, secure handshake protocol that is computationally inexpensive and suitable for detection of IoT devices of any computational complexity for the purpose of device discovery and device management. A physical unclonable function is used in securely generating a session key by the IoT clients, the IoT devices. An autonomous anomaly detection, whitelisting and blacklisting approach is proposed to prevent unwanted or malicious devices from joining, rejoining, or remaining in the IoT network. IoT, we have also performed a network simulation to test the effectiveness of our proposed system model. And I will also be sharing some of the results with you, where a CoAP server in the network performs real-time anomaly detection using our pre-trained machine learning algorithms. Before continuing, I would like to give a brief information about what physical unclonable functions are and how they work. They are basically circuits which can be implemented using a lot of different hardware already available inside IoT devices. And for example, an SRAM can be used as a physical unclonable function. Even an FPGA can be used as a physical unclonable function. And how they work is that for a given input, which is called a challenge, they produce an unclonable output, which is called a response, that serves as a unique identifier for that specific device. And the response generated by them can also be called as the digital fingerprint of that circuit, because it cannot be generated for a given challenge. Only a certain PUF can generate the same output. It is unclonable, it is unreforgeable, and this is the result, this behavior is the result of randomness, which is generated at the manufacturing phase of these chips and circuits. And it cannot be predicted and controlled, and as I said, replicated. And these features of physical unclonable functions makes them suitable for a lot of different security and cryptographic applications and problems. And in our case, we used physical unclonable functions on the client side, the IoT client side, because using them is very lightweight. Getting an output from a physical unclonable function, a circuit, requires almost no computational power or resources, and therefore they are suitable for lower complexity IoT devices. I would like to talk a little bit about the literature survey which we have performed and similar work. I have a table here which compares our research with similar papers, and I would like to go through the important features I have here. The first is that the protocol needs to be lightweight. Of course, as I mentioned before, not all IoT devices have the same computational complexity. So if you want to include all devices from all ranges, the protocol needs to be lightweight. And also, it is also important to not use any pre-shared secrets or keys. If you want to use the protocol in dynamic networks where a lot of new devices are coming in and a lot of old devices are leaving your network, which is often the case in real life systems. It is not feasible to insert a pre-shared key or secret inside every new node that wants to join to your network. And finally, blacklisting and whitelisting using autonomous anomaly detection. This ensures that the security of the IoT network can be maintained even if there are malicious devices present inside the network, because any device can initiate the network handshake protocol and join to your network. So you need to have some kind of a measure against these devices. And finally, experimental work is important because it is an indicator that the proposed system model and the protocol can easily be adapted to real-life scenarios. And in our case, we performed experimental work in the form of a network simulation to test the effectiveness of our proposed system. Now I would like to share the scheme of our proposed system model, as you can see here. It is a centralized network where a central CoAP server, where there is a central CoAP server and the IoT devices connect with the central server. There is a third party, a certificate authority, and the certificate authority is used by the IoT devices to authenticate the CoAP server. And some of these devices, as you can see, are actually, in fact, malicious devices, and they act like a benign IoT device, and they join to your network. And the malicious devices are not known by the CoAP server. So the CoAP server uses real-time autonomous anomaly detection to prevent these devices from remaining inside the network and blacklists them. We have a threat model. We used the Dolev-Yao threat model, where the malicious devices inside inside our system can listen, replay, and create messages inside the network. And their goals are to generate or obtain the key used in the sessions, to acquire device information, and to also obtain the confidential information shared within the communication after the secure session has been established. Now I would like to present our proposed handshake protocol. I have a sequence diagram, which I would like to go through with you, message by message. The protocol is initiated by the IoT nodes, the IoT devices, clients, with an hello message, very similar to the TLS handshake protocol, if you're familiar. And this first message includes the client's ID and a random number, the CN0. After receiving the first message, the CoAP server first checks the client ID against the blacklist to see if this device has been blacklisted before. If it is not, then it generates its own random number, the SN, and then it also generates a challenge by XORing the client's random number and its own random number. And it sends these back to the client with an hello message of its own. This message also includes the certificate of the server, which the IoT device will use to authenticate the server. At this point, the server tries to compute its own random number back by XORing the challenge and the server's random number to validate that the server actually used the random number sent by this device in the first place. And if it cannot, then this may mean a lot of things. This may mean that the server has been compromised, or this is not the real server. This may be a malicious server trying to impersonate the real server. So in such a case, the client terminates the protocol. But if it can, it will generate the second random number, the CN1. This is just here to show that the communication between the IoT device and the certificate authority is live. And it is also important to mention that the communication between the IoT device and IoT devices and the certificate authority is assumed to be secure. And it's the security of that channel is not within the scope of our security analysis. Moving on, the client sends the certificate of the server to the certificate authority for validation. The CA validates the certificate and returns an OK or a not OK message. Not OK meaning that the server cannot be trusted, and an OK means that yes, this is the real server. And if the IoT device receives an OK message, then the protocol continues to its second phase, where now the IoT device will generate the session key, which will be used in the session using its physical unclonable function. And its input is the challenge sent by the server in the second message here. And the IoT device will also receive the server's public key and send the generated session key to the server in message 5, which is encrypted using the server's public key. It also includes the challenge. At this point, the server decrypts the session key using its private key, and it also generates a session ID to identify the session which will be shortly generated. And the session ID is created using the client ID, the challenge, the session key, and it also includes a random number added to the end. And at this point, the server sends a final finished message to the client, and this message is now encrypted using the session key. Now this is symmetric encryption. And after receiving this message, the client also sends a finished message, the message 7. And now this message 7 also includes the information about the device, some specifications about the device, which will be used for device discovery by the server. And at this point, the server checks for the whitelist for the specifications of the device to see if it can be added into the IoT network. And if there is no problems, the client will be added to the IoT network and a secure session is generated. That is roughly how the protocol works. We have also performed a security analysis based on our assumptions. Our protocol provides 5 guarantees, and I would like to go through these guarantees briefly with you. The first is that the protocol guarantees that the generated session key is known only by the protocol participants. The protocol also guarantees mutual authentication. And also it guarantees that a secure and a unique session key is generated for each session. The generated session is guaranteed to be always with a trusted server. And finally, the secure session is always established with the client that generated the session key. This is for the server side, this guarantee. And now, as I have also said before, any client or any IoT device can initiate the handshake protocol and join to your network. So you need to have some kind of a security measure against such cases where you need to be able to detect malicious devices or devices that are generating anomalous network traffic inside your network to protect your network. For this purpose, we propose a real-time anomaly detection, which is performed by the server. And to test the effectiveness of our proposed system model, we performed a network simulation. And before sharing with you our results, the results of the network simulation, I would like to talk a little bit about our simulation setup. We have used 30 IoT devices to simulate the IoT network. The first 18 devices are low complexity IoT devices, such as controllers, hubs, smart cameras, monitors, or sensors. They are all benign devices. And the other devices are high complexity IoT devices. 5 of these devices are in fact malicious devices, which is not known to the server. And the server is expected to successfully blacklist all of these devices by the end of the simulation. And to train our classifiers, our machine learning classifiers, we used the IoT ID20 dataset as our main source of data. The IoT ID dataset comes with a pre-performed feature extraction and processing, therefore it was relatively easy to use. I would like to go over the classification labels available on the dataset. The first is the binary normal or anomaly. The second is a little bit more specific, the category label, which includes 5 different classes, and the subcategory label, which is more specific, which includes 8 different classes. For the purpose of for the machine learning classifiers, we have considered these classifiers, and for the purpose of real-time anomaly detection. And these classifiers were considered because of the needs and the constraints of our proposed system. And if I may, I would also like to share with you some of the results. Here you can see the macro average performances of our classifiers trained on the category label. This is a 5-class classification problem. And the amount of different class instances on the dataset were somewhat imbalanced. And therefore, the training data was chosen so that the amount of class instances would be balanced. Therefore, we used the macro average performances here. And if you take a look here, you can see that the stacking classifier, the decision tree, and the random forest classifiers performed the best on the data, where the stacking classifier performed a little bit more, performed a little bit better than the other two. And if we take a look at the subcategory label, the performances on the subcategory label, the difference between the stacking classifier and the decision tree and random forest classifiers is a little bit more visible here. The stacking classifier performed by far the best. And for our in our simulation, we used the stacking classifier. You may think that the stacking classifier is an ensemble classifier, which is correct, and it requires more computational resources than the other two classifiers. In our case, there was no issues by using the stacking classifier, but if the network traffic inside the IoT network would be so much that the server cannot handle the load, other classifiers such as the decision tree and random forest classifiers, even though they performed a little bit worse than the stacking classifier, they may be preferred. Here you can see the performance of each classifier on each class instance on the subcategory label a little bit better. And here I would just like to point out that the stacking classifier performed by far the best at detecting some of the specific classes, such as the scam port attack. As you can see, the stacking classifier is the best at detecting the scam port attacks. And for the purpose of blacklisting, of course, you may think that it is just enough to detect that if a if a package is just an anomaly or not, and you would be correct. But we chose to use the subcategory labels in our simulation, on the server side, because even after detecting certain attacks, you may want to have some predefined measures against specific kinds of attacks so that the server can better maintain the security of the network. For the network traffic generation, we used a Poisson distribution to simulate the network traffic. It is widely used for network and communication traffic simulations. And for our simulation, each device sends, on average, sends 3 packets per second, each client. And here you can see another graph which shows the number of packets sent at each second. The initial spike is due to each device performing the Handshake Protocol. After the initial spike, the number of packets sent at each second converges at around 36 packets per second. And this is also due to the fact that our whitelisting policy in our simulation was that we only accepted high complexity IoT devices into our network. So we had 12 high complexity IoT devices, and they all generate on average 3 packets per second, and therefore it converges at around 36 packets sent per second. We have also performed a latency test, and I have a latency comparison here, which I compared the latency of our protocol with the TLS's average latency. And based on our measurements, our protocol appears to be faster than the TLS handshake protocol. But mind you, this is TLS 1.2, not 1.3. To conclude my presentation, we presented a proposed a secure handshake protocol, which is lightweight, which utilizes physical unclonable functions for the purpose of session generation and device discovery on IoT networks. We have used autonomous anomaly detection using machine learning for blacklisting. And we have also shown the resilience of our protocol against various attacks with our simulation results and security analysis. And finally, the stacking algorithm is shown to display the highest level of accuracy with an accuracy of 99.98% in detecting anomalous network traffic. And for our future work, we are currently working on a more detailed trust score-based blacklisting algorithm, which will be used by the server to detect malicious devices which generate which only generate small amounts of anomalous network traffic to avoid detection. We are also doing an in-depth comparison between other IoT fingerprinting techniques for authentication, which will be compared with our physical unclonable functions. We are currently making a comparison between the TLS fingerprinting techniques. And finally, we are also working on other network simulation, which uses a distributed IoT network where there are multiple servers, and also a network simulation which includes channel fading, noise, and packet collision. Thank you so much for listening. And if you have any questions or suggestions, I would be glad